So in this video we're going to be talking about velocity time graphs. We're going to introduce the concept of acceleration. We're going to calculate with an equation, and we're going to learn how to calculate it from the graph, from a velocity time graph. We're going to introduce our acceleration equation. So acceleration is the change in velocity over the time, and we'll talk about the units involved in that equation. We'll also look at it in symbols, and then we'll look at how we can also calculate the distance travelled from a velocity time graph. As always, remember to use the pause button, make summary notes, bring any questions to the lesson. So let's get a velocity time graph to work from. So let's imagine an object, it's travelling in a straight line, and we can show the velocity of the object on a velocity time graph. Remember, velocity is a vector, it has magnitude and a direction. So you can see some of these values here have got a negative value for velocity. That's because it's travelling in the opposite direction. So you might imagine somebody travelling to the right has a positive velocity, and somebody travelling to the left has a negative velocity. Grab a bit of graph paper, plot this graph, try and make it take up as much as of the A4 bit of graph paper as possible, and then when you've got the graph finished, have a look at the graph on the next page and see if you got the right thing. We're going to plot velocity on the y-axis and time on the x-axis. So hopefully you've got a velocity time graph that looks a little bit like this. You can have a look at the scale that I've chosen here. We've got our negative numbers and our positive values of velocity. We've got this labelled with units. We've got our x-axis labelled with units. And because it's a journey, we're essentially joining up the dots rather than doing a line of best fit. Now, just like we saw with a distance time graph, the shape of a velocity time graph can tell us things about the motion of a journey, but the shape of a velocity time graph means something very different to the same shape line on a distance time graph. So the first thing you must do is check whether you're looking at a velocity time graph or whether you're looking at a distance time graph, and remember the differences between the two. If you have a horizontal line on a velocity time graph, that means something's travelling at constant velocity. But if you remember back to the previous lecture, we said that a horizontal line on a distance time graph would mean that something was stationary. So here on a velocity time graph, if it's got a horizontal line, that means it's travelling at a constant velocity. If it's got a horizontal line but with a negative value, it means it's travelling backwards at a constant speed. If we've got a straight line like this but that has a gradient to it that we could calculate, that means the velocity is changing, and so we're accelerating. Here the velocity is getting bigger with time, so we can say it's accelerating. Here the velocity is getting smaller with time, so we could say it's decelerating. So here's your velocity time graph that you plotted previously from your data. And what we're going to do now is we're going to label the different sections of the graph. So you start off with labelling sections of the graph where we've got a constant velocity. So we've got a constant velocity on this section here. And we've got constant velocity on this section here. We've got, if we look for areas where we've got constant acceleration, we've got constant acceleration here. If we highlighted areas where we are not moving, where we're stationary because the velocity is zero, we're stationary here, we're stationary for a moment here, and we're stationary here. Now, for the next bit, we have to be really clear about what we mean by acceleration and deceleration. Deceleration is that our velocity is decreasing in magnitude, so it's going towards zero. The term acceleration can be used to describe accelerating where the magnitude of the velocity is increasing, and it can be used to describe decelerating as well. So just is the velocity changing, in which case it's accelerating. So technically all of this section here and this section here, you could say that you're accelerating because the velocity is changing. And there's nothing wrong with that at all. If we have a little think about whether the velocity is getting bigger or smaller, here the magnitude of the velocity is getting smaller, and here the magnitude of the velocity is getting smaller. So you could say that you've got constant deceleration here and here. And on this section here, because the magnitude of the velocity is getting bigger, you could say that you've got constant acceleration, but really important to realise that because we've got negative values of velocity, we're travelling in the opposite direction. So what's happened is we've started from stationary, we've then accelerated with constant acceleration, travelled at a constant velocity, then we've started decelerating at a constant rate, and then we've slowed down until we've stopped for a moment, and then we've started accelerating in the opposite direction, travelled backwards at a constant velocity, and then we've started decelerating until our velocity is then zero again, and that's the end of the journey. Okay, so next we're going to look at how we can find the distance travelled during a journey from a velocity time graph. We know from our previous lesson that distance equals speed times time, and if we write that in symbols, remember we're representing distance with the symbol s, displacement with the distance and displacement with the symbol s, speed with the symbol v, and time with the symbol t. This is a velocity time graph, so the y-axis is velocity and the x-axis is time, and you can see how that links here. Yeah. So if we multiply a value from the y-axis by a value from the x-axis, we're going to get an area. Yeah. So the area under this graph represents the distance travelled. Now, they're not going to give you massively complicated shapes to do this with, but you are going to use the understanding that you have from maths about the area of different geometric shapes to work out the area under the graph. So let's have a go. So what you're going to do is you're going to break large areas down into right angle triangles and rectangles. We know that the area of a rectangle is the base times the height, and we know that the area of a right angle triangle is half the base times the height. In terms of the numbers that we're putting into the base and height, we have to read them off the scale. You're not simply putting in the number of squares, you're taking a reading off the x and y axis. So here I've got a trapezium shape, I add some lines in, so I've got one rectangle and two triangles. I work out the area of each individual shape and add it all together. So the area of A is half the base times the height, the area of B is the base times the height, and the area of C is again half the base times the height. So here I've put some pretend numbers in, and you could say that you can see what we've done. So the area of A is half. If you take this value here to be 20, and if you take that value there to be 10, sorry, this value here to be 20 seconds, we do half times 20 times 10 for the area of B. This would be 20 and this would be 60, so between there and there would be 40 times the height of 10. And then finally for C, this we said was 60, and this is going to be 70, so we've got 10 times half. Add these three distances together, you get total distance travelled of 550 metres. The numbers are on the previous slide, if you go back and have a look at the previous slide. You could go and now try this for the first section of the velocity time graph that you plotted to check that you understand what you're doing. Sometimes we have a graph and it's not a nice geometric shape that you might have learned how to calculate the area of in maths. So here's an example of graph being plotted from some data. They might say calculate or estimate the distance travelled from this velocity time graph. If you don't have a nice geometric shape like a rectangle or a right angle triangle, what you can do instead is you can use the counting square method. So we use it if we've got curved lines and more complex areas. First of all, count the whole number of squares, then add in the squares where the majority of the square is under the line. So you've got a total number of squares in this area under the line here. Pardon me. And then you need to convert the number of squares into a distance using the scale. So if we have a look at this scale here, if we're looking at tiny squares, if 10 squares equals 2 seconds, then each little square is going to equal 0.2 seconds. If these 10 squares here equal 1 metre per second, each little square is going to equal 1 metre per second. So you can then work out the area of one little square and then times that by the number of squares and then go from there. Right, so let's talk about acceleration. Acceleration is a vector quantity. It's measured in metres per second squared. We're going to use the equation acceleration equals the change in velocity divided by time. If we look at that in symbols, we're going to say that A is equal to delta V divided by T. This equation is not given in the GCSE. You need to memorise this equation. A stands for acceleration, measured in metres per second squared. Delta V, the change in velocity, measured in metres per second. And T is the time measured in seconds. The change in velocity is the final velocity minus the initial velocity. If an object slows down, it's decelerating, so you'll get negative acceleration. So as well as calculating the acceleration using the equation, we can find the acceleration from a velocity time graph. We know that the gradient of a straight line on a graph is delta y divided by delta x. The gradient of a velocity time graph tells us the acceleration, and we can use that thinking about the gradient again. So delta y in this case is velocity, delta x is time, so the gradient is velocity divided by time, the change in velocity divided by the change in time. That was what our definition of acceleration was. Now we looked at calculating the gradient of a line in the previous lesson, but just some quick notes to remind us. We need to draw our triangle in between 2 points, find the change in y, read it off the scale, find the change in x, read it off the scale, find our ratio between those two, and then remember to add units of metres per second squared. A couple of things to bear in mind. This section here of the line, we know from maths, is going to have a positive gradient. The velocity is getting bigger, so we've got positive acceleration. This section of the line here has got a negative gradient, so you are going to get a negative acceleration. It is getting slower. We can also use the tangent method that we learnt from distance time graphs. So if we have a curvy line and we want to find the acceleration at one particular point, we draw a tangent to the line and then find the gradient of that line. So why don't you have a go now of finding the gradient of this section of this line, and then we'll go through the answer together. So I've drawn in my triangle here. This is going to be delta y. This is going to be delta x. I read the values off between here and here from this scale, and I get this is a value of 10. This value here, that's 10, and this is 0. So delta y is equal to 10 minus 0, so delta y equals 10. If I look at the change in x, I've gone from 0 to 10. So delta x equals 10. So then the gradient is delta y divided by delta x, which is equal to 10 divided by 10. That gives me 1, but I need to add units in. I'm finding an acceleration, so metres per second squared. Right, so there we have it. We've looked at velocity time graphs. Remember that we can use the area of the velocity time graph to find the distance travelled. We can use the gradient of the velocity time graph to find the acceleration. Acceleration is equal to the change in velocity divided by time. If we write that in symbols, we've got A equals delta V over T. This equation is not given and must be memorised for the exam. The shape of the velocity time graph can tell us about the journey, but remember it tells us different things than for the shape of a distance time graph. So if I was going to give you one piece of advice for the exam, always make sure you check the axes properly before you start answering the question. Bring any questions you have to the lesson, and I will see you in the next video.